Yeah, next to electrochemical technique is coulometry. Okay, coulometry also as name indicates, you measure the coulombs. That's the charge, number of charges, and then you based on the coulombs, and the analysis is done. Okay, and this coulometry is really precise the method. One of the most precise in the techniques in analytical technique. Okay, so this coulometry is so precise. So sometimes the Faraday constant, historically Faraday constant was determined by this coulometry. Okay, so this coulometry is a form of chemical analysis based up on counting the number of electrons used in a chemical reaction. Okay, actually Coulomb is what? This charge. Charge is the current flows, and current is what? By definition, current is the charge flow, yeah, with respect to time. Okay, so if you divide the charge by the time, that's the current. Okay, so in other words, to calculate the Coulomb, the total charges, and you simply multiply the current and time. So if the current is not constant, and then you integrate current, yeah, over the over a certain range of time, yeah, that's the Coulomb. Okay, and then taking an example is the best way to learn this coulometry. Okay? Here is the example. The cyclohexene here. Okay, cyclohexene is readily react with bromine. Bromine. This is not gas. This is in the liquid form. Okay, and this bromine react with the cyclohexene here, and then this is the compound we obtain. This bromine atom now added this is additional reaction to this double bond, and then it is trans to each other. Okay? So trans 1,2 dibromocyclohexane. Yeah? And now instead of taking bromine liquid and inject into cyclohexane, but we can't generate this bromine, okay, by the oxidation of bromide, okay, electrochemically, okay, yeah, and this one, this is actually it's a two reaction, okay, as you generate this bromine, and then in the presence of cyclohexane, this reaction goes on automatically inside this spontaneously, okay. So this is a setup of that experiment. You take this round bottom flask with three necks, okay, and then in this neck you insert two electrodes, okay, to apply the constant current. As I said, mm, uh, you can apply the potential, or you can apply the current to induce, okay, the this electrochemical reaction. Okay, but usually people control the potential. But in this example, by applying the constant current between these two electrodes, we can induce this bromine bromide oxidation. Okay, and this neck, that's the port for adding reagents. Okay, and there is another set of electrodes. Yeah? These two electrodes is the indicator electrode to what tell you when this reaction is complete. Okay, you know, let's think that now you keep by adding, by applying the constant current, and then you keep producing this bromine, okay, and then bromine is keep reacting with the cyclohexane, okay, yeah. But you want to, the now question is the uh, want to know the cyclohexane concentration, and then you want to stop this reaction, you know, immediately after this cyclohexane is being completely consumed. Okay, so you know when this cyclohexane uh, is consumed. Okay, otherwise, although this there is no more cyclohexane in the solution, but you may keep generating this bromine. Okay, that's not what you want. So you have to decide, okay, when to stop. Okay, in other words, you have to decide when the cyclohexane is completely consumed, right? Yeah, this electrode says that. Okay, then this one you put applied this variable, this is the variable power supply, and then you measure the current. Okay, I will show you soon. Okay, now you understand that this electrochemical setup. Okay, this is done by the constant current method. Bromine generated a platinum anode, then reacted with the cyclohexane. Okay, after cyclohexane is consumed, bromine here suddenly rises. Okay, signaling the end of reaction. The rise, current rise is detected by measuring current between these two platinum electrodes. Okay, the 0.25 volt was already applied. Okay, this the current, there will be no current in the presence of cyclohexane because this bromine is already consumed, immediately consumed. But when this cyclohexane is no more there, and then there will be bromine. Okay, and then this bromine may be reduced at one of the this platinum electrode, and then current will increase here. Yeah, so by taking a look at this microammeter, yeah, and then you decide when to stop. Not enough to electrolyze any solute, very tiny current of what less than 1 microampere flows. Okay, in the presence of cyclohexane. At the equivalence point, the bromine suddenly increased. Okay, detector current will increase. Okay, there's a detector at the detector anode. This bromide is oxidized, and detector cathode, and this bromine is reduced. All right. Yeah. So by uh, what? By taking a time, okay, from start to the end, and then since you applied already the constant current, the charge is what? The current multiplied by the time. Yeah, that's the charge. And here calculation is that the cyclohexane, this amount of this one you want to calculate. So but actually you simply generated not this one, bromine. So one bromine, um, this molecule reacts with one cyclohexane molecule. Okay, so but to generate this one bromine, you need two electrons. Okay, but this one bromine molecule is generated from two bromide ion. Okay, so actually one bromide ion is corresponding to uh, one more one bromine molecule, and this one bromine molecule reacted with this one. Okay, so in other words, this one bromide, okay, mm, is equivalent to what? This one molecule of cyclohexane. Okay, here is an example. But here's a reality. Enough bromine is first generated in the absence of cyclohexane. Okay, whenever the cyclohexane is consumed, and then immediately there will be extra bromine, this molecule, mm, and then the current here, this emerged current will suddenly will increase to about 20 microampere, yeah, from less than 1 microampere, and then you can stop. Okay, there. Uh, Bromine, but if when cyclohexane is added, the current will decrease because this extra bromine now reacts with cyclohexene. Okay. Bromine molecule is generated again, and then end point is taken when the detector again reaches this amount of current. This 20 microampere. This is arbitrary current, but the point here is that you take you determine uh, the time when the current increases a lot. Okay? Because the reaction is begun with bromine present, impurities that can react with bromine before analyte is added are eliminated. Okay, so you have to be careful whether the, any impurities there. Okay, here is an example: a 2.000 milliliters volume containing this amount of cyclohexene per milliliter, yeah, 0.61113 milligram cyclohexene per ml. So in 2 ml, yeah, there will be 2 times of this amount of cyclohexene is titrated. By the way, this is called coulometric titration. Yeah, okay. It may sound strange to you, but yeah, yeah, that's the correct name. This is coulometric titration without burette. Okay, and so what is analyte in this case? Yeah? Actually, you inject, yeah, not liquid but electrons. Okay, electrons are analyte here. Anyway, this is called also the coulometric titration, and with this amount of current, yeah, this is current you generated very precisely. How much time is required for complete titration? Yeah, this is rather simple example, but the cyclohexene quantity is what? This one, this milligram now converted to mole. Okay, cyclohexene, formal mass is this one, 82.146 milligram per millimole. Okay, and then this one here in 2 ml, the solution, cyclohexene amount is 2 times of this amount. Okay, so you multiply by 2, and then you get the number of moles of cyclohexene is 0.01488. In this case, millimoles. Okay, and the number of electrons is what? Number of electrons here. This is reaction. This is reaction. The 1 mole cyclohexene corresponds to 2 moles of bromine. 2 moles bromine now corresponding to 2 electrons. But these 2 electrons is made from actually it's a bromide. Okay, the oxidation of bromide. And then 2. So actually 1 um, cyclohexene corresponding to 1 mole of bromide. Okay, so 1 mole of this one electrons. Okay, so moles of electron is what? Using this one here, and then time is given by here number of moles of electrons multiplied by Faraday constant and divided by current. Yeah? And then this is moles of electron is what? This one here, number of this is cyclohexene um, mole, and then 1 mole of cyclohexene corresponding to 2 moles of electron, so you multiply by the 2, and this number, which is 0.02976 times 10 to minus 3 mole, and then Faraday constant, which is 96,485 coulomb per mole, and divided by this one current, yeah, this one. And then you get about 600 second, 5, this one, 595.1 second, right? Yeah, as you see here, this technique is very, very precise. Yeah? You can get, you have to measure current or time, you know, as precise as possible, right? Here, there are several important advantages of coulometric titration. First, that technique is very precise. It will give you the precision and sensitivity and generation of unstable region in situ. You know the in situ. In situ means what? Situ means that's the place. Okay, in situ. Yeah? Uh, Now you want to produce a very unstable region, yeah? But in the by other method, yeah? The region unstable region is so unstable, so that's lifetime is very short. But with this colorimetric titration, and then you generate this very unstable region, and then that region will immediately react with the reactants in solution. Okay, in situ means everything in the same space. All right. um, and then the colorimetry can be used. Okay. So there is a commercial colorimeter available in my lab. I bought one. So commercial colorimeter gives you 0.1% error, right? This is a very precise, but with much a more expensive instrument, you can do much better. Okay, maybe 0.001%. Okay, so as I mentioned, the Faraday constant, even Faraday constant, was measured using this colorimetry. Okay? So with colorimetry, you can generate protons, hydroxide ions, and silver ions or iodine to titrate, unlike including CO2, sulfite in food, sulfide in wastewater. Okay. And also you can generate unstable regions in situ, such as this one, silver divalent cation. Now this is very unstable. Yeah, so in ordinary way it is not easy to produce this ion, but with colorimetry it is possible by oxidizing this one, the silver ion, this copper, this plus one state. This is not very unstable, yeah, but not common. Okay, monovalent copper ion, very easily can be produced with this colorimetry. Okay, and manganese 3 plus this ion is unstable, and titanium, the trivalent titanium ion is unstable, but no problem to produce these ions colorimetrically. Okay? And here is the types of colorimetry. Okay, colorimetry can be done at a constant current or at a controlled potential. Okay, either way. Our previous example was done by at a constant current. Okay, but you can apply the potential, or you can change the potential. But usually people apply the constant potential to do the colorimetry. Okay. Constant current colorimetry is simpler, I think, but the one big problem is that you have to decide when to stop. Okay, you can keep, the flowing the current. Okay, and then although the analyte is completely consumed, still, you can apply the current. So you have to know when to stop. Okay, you have to know exactly when the equivalence point is reached. Okay. In the meantime, controlled potential colorimetry is done by at in a three electrode system. Okay, this is very important. As I said, if you made a two electrode system setup, and then when you applied the constant potential, but as you saw, the one of the electrode potential change a lot internally. Okay, so the controlled potential colorimetry is very good technique, but you have to employ a three electrode system. Okay, this is absolutely recommended. Okay, yeah, all right. And then one of the advantages of this controlled potential colorimetry over constant current colorimetry is that you don't need to worry about when to stop. Okay, since potential is controlled, yeah, and then when the reactant is all uh, consumed, and then current will drop to zero. Okay, so you don't need to worry about that when to stop. Yeah, you just let the time goes on enough. Okay, and then what you need to do after the experiment, you integrate the current with respect to time, and then modern instruments can do that for you. Okay, so you don't need to worry about that here. this total Coulomb is the integration of current with time over a certain range of time from 0 to t. Right? Okay, let's stop here.